Thanks everybody for coming to my talk. Thanks to the conference organizers for all their hard work and for accepting my proposal to give a talk about computer vision using Ruby and libjit. Okay, a footnote. 2 days ago I conveniently broke my glasses, so if I cannot recognize some of you at 1,000 meters distance, please don't be offended. Most of this work was done in context of the EPSRC nanorobotics project, which is a research project in UK, and it was about implementing a vision-based closed-loop control for inner transmission electron microscope, and the work is all released on RubyForge among other websites under the name HornetsEye. The link to the slides is for some reason is not visible. Sorry about that. But I put the link on the RubyConf website as well. So while I did this work in context of the nanorobotics project, the intention is to write a general purpose machine vision library. So here are a few example applications of computer vision. I don't have time to go into the details. But what I want to show today is a bit of augmented reality, because many people, they get stuck on doing two-dimensional computer vision, and because it requires a bit of a step to go into 3D, but once you have taken this step, you can do so much more. It's very interesting. By the way, the slides, I'm changing them using a camera as well. So this presentation software is all written in Ruby. So when my hand comes here, I can choose slides using a camera. And because I'm nervous and my hand is shaking, so I also added some functionality, so I can just do this. If I do this, it'll just go one slide forward, like this, go one slide backward. Okay. All right. But computer vision means array operations. It's really like this. A lot of it is done using array operations. And as you can see here, even the recent version of the Ruby virtual machine is still 30 times slower on this particular machine than the recent version of GCC. So this is an example of an operation creating an index array with 10 million elements. Yeah. So you may think maybe using Ruby is not such a good idea. I don't know who of you have seen the movie, but if you've seen the movie iRobot, you know what that red light means. So I said, okay, doesn't matter, I'll do it in C++. I'm very good at C++. So I wrote, for example, a plus operator for the boost multi-array class, which is the class of choice if you do n-dimensional arrays in C++. And actually it turns out it's quite a lot of code just to implement a stupid plus operator, an element-wise plus operator, because it turns out the very data types which are most important for your work are arrays and integers and floating point numbers, and all these types are basic types in C++, so they have the worst support from the language. And if you do the same thing in Ruby, you can, with less than 10 lines of code, you can have a working version of an array operator already, which runs on multidimensional arrays. So the trick is in order to combine performance and flexibility, I used an approach similar as the NArray library, that you basically implement a Ruby extension providing uniform arrays, so arrays where each element has the same data type, for example, a duck. But I'm not using NArray. I'm implementing my own extension because, for example, NArray is written mostly in C, and it's, for example, not easy to add a custom element data type. Now I'm going to show you how this is done. It's actually not very difficult. The core of the library is very small. So you start by defining a C extension, which defines a class, a malloc class, And this malloc class, you use it to, for example, allocate 10 bytes of memory, and then you can write a Ruby string to the memory, or you can read back 5 bytes of memory and get the content as a string. And you can do pointer operations like m+2, and if you read 5 bytes then, it'll ignore the first 2 bytes. Of course, you have to be aware of the problem that like this is not safe against buffer overflows. So if you read 10 bytes after increasing the pointer, it'll crash. So you have to reintroduce boundary checks at a later stage, but this is part of the thing which saves a lot of time, which makes a lot of performance. And so you can use this class to define a native data type in Ruby. So the constructor, you allocate 4 bytes of memory, and then you have a set and a get method. I don't know, maybe some of you were in the talk earlier on. So you just use the standard Ruby library methods, array pack and string unpack to convert a Ruby integer into a 4-byte string containing the native representation of that integer and back. And so then you can write a native integer, and on the right side of the slide is some example use where you create an integer with initial value 3, and then you set it to 5, and you can read back the value. And you can make all this, you can do all this in a more generic fashion, so you can make a more generic integer class, a parametric class, if you will, which has parameters, a number of bits, and signed or not. And then you create a method which creates classes inheriting from that class. And on the right side, you can see the purpose of this. So I say, for example, unsigned short int is an integer with 16 bits and unsigned. And if you have taken care about choosing the appropriate descriptors and memory size and whatnot, then it'll behave as expected, and you can straight away start using this integer. Also, what's useful to implement is some means of having several Ruby objects viewing the same memory location. And in the same fashion, you can implement static arrays. So in this case, you have a parametric class with parameters, number of elements, element type, lm, and number of elements, and stride. And stride you can assume to be 1 at this point. And selecting an element basically means taking the pointer, adding I times the size of an element to it, and then creating a view which is viewing that part of the memory, and the view is of the element type. And then you can use this to implement the standard Ruby array operators. And on the right side is some example code where I say, okay, a short integer is a 16-bit signed integer, and then I create an array with 8 elements of that type. I fill it with the default value, and then I can set and retrieve elements as you would expect from an ordinary array class. And if you have implemented everything properly, this will work multi-dimensional straight away, so you can create an array of arrays. So you say, in this case, a 32-bit integer array, a 3 times 2 array. And if you implement some inspect methods to do some pretty printing, it'll pretend to be a multi-dimensional array. And you can also add, improve your methods for selecting elements so that they will accept multiple indices or even ranges as indices in a similar fashion as the NArray library provides. In contrast to NArray library, this will create a view on that memory, not a copy actually. So now we have arrays, and the next thing is to define operations on them, and I will show you how to implement how I implement unary and binary operations. Of course, there are more array operations than this. So we start with scalars, and I just define a method called op, and the method passes its arguments to instance exec. It just calls instance exec, nothing more. And then you can already use this to define a negate operator. The negate operator just creates a new object of this class, and then it calls op with the Ruby value of this native element as a parameter. And the operation you execute with instance exec is just does set minus x, so set to the negative value, and that's all. And on the right side, you can see an example where it works as expected. You create a short integer with value 3, and minus s will give you a short integer with value minus 3. And then for arrays, you also define the op method, and it simply loops over all the elements and calls op recursively. And if one or more arguments are arrays as well, you also iterate over the elements of that array. And if you do it like this, you can actually implement the negation operator exactly the same way as for the Scalar. And on the right side, you see some example usage where I create an index array with values 0, 1, and 2. And if I negate that array, I get 0, minus 1, and minus 2. So this is all nice and good, but it's still very slow. So how to speed up things? Okay, if you look at the title of my talk, you can already guess that we're going to use libjit to do this. And I also use a reflection to do this. So I use a reflection to compile code, to interpret code. So you start with this is an example illustrating this, where I use, this is a small class which uses method missing to record what methods are being invoked on an object of this class. On the right side, you can see some example use. So I create two objects of this class, A and B. And as you can see, if you do operations on them, it will faithfully record what's happening. Of course, Ruby reflection has some limitations, so you have to restrict yourself to a subset of Ruby when doing this. So you can see there are a few operations where you won't be able to distinguish what's happening. And then you integrate JIT like this. So this is for Scalar operations. We implement a new op method, and the op method will first check is self and all the arguments, are they all JIT supported? And if yes, then we call the JIT compiler and give it all the variables, self and the arguments. And the JIT compiler will convert the variables to JIT variables and call this code block which I'm passing here. And in the code block, I just call the method itself again. So I'll enter again at the top. And because JIT variables themselves are not JIT supported, I'll jump into the second case. This will call the old implementation of the op method, which will call instance exec in turn. And to understand what happens, you can, for example, implement a negation operator and add some print statements to it. Then you can see that when executing the operation, you actually don't have ordinary Ruby variables, but you have actually JIT variables. So you have self is an integer with the value the machine register I1 is pointing at, and the parameter x is another register. And when you do set minus x with this variables, then instead of doing computations, it will generate machine code. So it will generate a code for negating and writing the value to a new register, and then code for writing the value of that register to the memory location I1 is pointing at. And this is actually inspired by ruby-libjit, which is another project using the libjit library. And for arrays, it gets a bit more complicated. Again, you initialize the same way. You check, do we have JIT support? You call JIT compiler, you call yourself. And then you jump into the second case. And then we check, are we JIT compiling? Yes. Then I first get a reference to the JIT function. And then I create a copy of the array pointer. I compute the strides. And I compute a pointer to the end of the array. And then I create, this is a bit complicated, I create a list of functions for the arguments to process the arguments. So if the argument is an array, I will add two functions, one function for incrementing an array pointer and one function for extracting an element. And if an argument is a scalar, then I just add a function for returning that scalar. And then finally comes the loop. So in the loop, I simply extract all the current arguments. I call op recursively, and then I increment all the pointers, and I do this until I have reached the end of the array. And here are some, what's this? Here's the illustration. So you see that very similar as with the Scalar operation, it's almost the same, only the register indices are higher. And this is because while we are generating the same machine code using the operation, the library will put some looping code around that operation. So you'll end up with a machine code to do the array element-wise operation. And here are some performance results. They vary greatly depending on the machine. So you can see it's still sometimes 6 or even worse, 6 times slower than C++. But if nothing else helps, I will just implement a small C++ code generator and use GCC to beat C++ with C++. I mean, it's no problem. And I also, to the comparison, I also added the NArray library. So we should at least be able to reach the NArray library's performance with this concept. And now I want to give an example what one can do with the library. So the question is, we have an image showing a rectangular marker, and we want to determine the position of that marker in order to be able to draw a coordinate system properly into that image as shown on the right side of the slide. I'm not showing you all the code. I will explain some methods instead of showing the code. But basically, you start with opening the camera, and then you read an image. Then you threshold that image. This is an example of an element-wise array operation. And then I do connected component analysis. In this case, we will have 93 components, including the background. So you set n to the maximum index of the component image plus 1. And then we create a histogram of the components. This will give us the area of each component. And then we create a mask, a binary mask, to filter for the components which have a size which is within the acceptable range. And then I create an index array, select just the indices which I'm interested in using the mask, convert it to a Ruby array, and then I can loop over the indices. So I'm now looping over the remaining components which are not too small and not too big. And C is the loop variable. And I can create a mask of the component by just saying components equal C. And then I can create a mask just selecting the edge pixels by taking the difference of the dilated component minus the eroded component. So I get a mask with all the edge pixels. And then I'm computing the gradient. So I'm not showing you the source code of this method, but it basically just computes the gradient vectors, which direction the gradient is pointing at. And for convenience sake, I store the gradients in complex numbers. So it's complex gradients. So the real and imaginary part are forming the two parts of the gradient vector. And then using a mask operation, I just select I create a one-dimensional array with just the gradients of the edge pixels. And then you see what I'm heading at. So now I try to detect dominant orientations. In order to do that, I compute the argument of the gradients. The complex argument is, in this case, the gradient angle. And then I quantize this into 36 bins. And I create a histogram. If this is a rectangle, you should end up with a histogram with 4 peaks. So I threshold this histogram. And then I look for connected components in the binary image, in the resulting binary image. So if this is a rectangle, I should end up with 4 components. And in the end, I also create an array partitions, which will tell which component each gradient is belonging to. And if I have 4 dominant orientations, then I assume I found a rectangle. And then I compute a complex ramp. I'm not showing you the source code of this method, but it basically is a complex array, a 2-dimensional array, with the real and imaginary part containing the x and y coordinate of each point. So you have a 2-dimensional array, and the first row will be 0, 1, 2, 3, 4. The next row will be 0 plus I, 1 plus I, 2 plus I. The third row will be 0 plus 2i, 1 plus 2i, 2 plus 2i, and so on. And then I do a masking operation to compute x, so that x will be a 1-dimensional array containing the complex coordinates, if you will, of all the edge pixels. And then the following 2 statements are just to compute the center of gravity of each line. So I first create a histogram of the labels. This will give me an array with the size of each line, the number of pixels of each line. And then I create a weighted histogram where I use the coordinates as weights. And if I divide this by the number of pixels each line has, I will end up with the center of gravity of each line. I also will get the center of gravity of the unclassified pixels, but I will ignore that later. And then I need to compute the orientation of each line. And in order to do this, I first subtract from each edge point, I subtract the coordinate of the corresponding center of the line. So I'll end up with vectors pointing into both directions along the line. And if I would just sum them up, I would end up with 0, so that's not useful. But these are complex numbers, so I use a trick. So let's say I have I have vectors pointing at 20 degrees and vectors pointing down the line 200 degrees. If I square the complex number, I'll end up with twice the angle. So I'll have now 2 times 20 is 40 degrees, and 200 times 2 is 400, modulo 360 is also 40 degrees. So now I can sum them up. After taking the sum, I take the complex square root, and I'll have my orientation 20 degrees. And if you do a web search for line fitting algorithms, I'm sure you'll end up with more source code than this. And then finally, I compute the intersection of each 2 neighboring lines. I'm not going to explain how I did this. This was a bit difficult. But basically, then you will get the corner points of the rectangle. So now you see we have gotten very far already. And now we want to do 3D. So what I want to be able to do, I want to be able to find a function where I can give that function the coordinate, for example, say minus 2.5 centimeters, minus 2.5 centimeters, and it will give me the top left corner in the image. Or minus 2.5 centimeters, and y is plus 2.5 centimeters, then it should give me the next corner. So now I'm looking for a function like this. So in order to do this, we need to do a little bit of math, but you will be surprised in 10 minutes, you will know how to do 3D vision. And we start out with, I guess everybody knows this, the pinhole camera model. The pinhole camera model just says the size of the object x1 divided by the distance of the object x3 equals the size of the image on the camera chip divided by the focal length. And the size of the image on the camera chip is the number of pixels times the actual size of a pixel on the chip. So delta S is the pixel size on the camera chip, and F is the focal length, and the ratio F divided by delta S you need to know. But you can, for example, do this using camera calibration, or maybe you can even get it from the specification of the camera. And This, of course, holds for both dimensions in 3D, so x1 to x3. You have an equation for the first dimension. You also have an equation for the second dimension, which gets projected. And now we take these equations, these two equations, and we reformulate them a little. And we introduce an additional variable lambda. And this is called homogeneous coordinates. Anybody who has done 3D graphics will be familiar with this. We just set lambda to x3 and add an additional equation that lambda has to be x3. And we require lambda to be non-zero. And the reason to do this is that this will allow us to write all these projection equations using matrix vector multiplications. So it makes it more easy to handle. And this matrix is actually the intrinsic camera matrix. This will do the projection for us. And then it's when you've done this, it's much easier to introduce additional 3D rotations and translations by just taking the point x1, x2, x3, the vector. We just multiply it with a rotation matrix, and we add a translation vector. If you also use homogeneous coordinates for the 3D point, and you do this by just adding an additional, a fourth element to the vector, which is 1. If we do that, we can write the rotation and translation using one single matrix multiplication. And what we will do now is we will insert all those point pairs of screen coordinate and desired coordinate. We have 4 of those pairs, so we'll insert those. Yeah. So bear with me. We also need to allow for an error. So now we have 4 of those equations, so I just write it once. So I is between 1 and 4 with the projection and the rotation and translation. And because our object is a planar object, the third coordinate is always 0, as you can see. So this allows us to drop one matrix column and the 0. So we'll end up with the equation in the second row. And then we will, for the moment, we multiply the intrinsic and the extrinsic camera matrices. And now we are going to look for the best matrix H, which is going to minimize our overall error. And now we get rid of lambda. So we take the last row and we compute lambda and then substitute the value. And you can see we have the unknowns H31, H32, and so on, multiplied with the error, so we can isolate the error. So what we do is we assume that lambda 1, lambda 2, lambda 3, and lambda 4, they're actually the depth of each point, so they don't vary too much. So we say these are weights for our error. If we omit those weights, we will not introduce too much of a bias. So instead we optimize for the non-weighted errors. And now you can see you can isolate the error easily. And so we have for I1, 2, 3, and 4, we have for each of these values, we have 2 equations. So the bottom row is basically 2 equations written in one matrix equation. And then we put all these equations into one big matrix. And now the problem becomes the problem of finding a vector H. So I've written the matrix in a stacked vector form. The problem becomes the problem of finding a vector H such that the norm of m times H is minimal. And in order to avoid the trivial solution, I mean, you could say H0 is the best solution. So in order to avoid this, we impose an additional constraint that H, the norm of H must be an unknown number mu, but mu must not be 0. And here comes the big mathematical trick that this is actually, the solution is actually the singular value decomposition. So I don't know, does anybody of you know the singular value decomposition? Or anybody knows eigenvalue decomposition? So yeah, so you can see, you can say singular value decomposition is a more generic kind of singular eigenvalue decomposition. So singular value decomposition you can also do on non-square matrices like this. That's all. And then the thing is, if you have a singular vector and you say m times the singular vector, if you multiply this, the length of the resulting vector will be the singular value. So you just take the singular vector with the smallest singular value, and then you will have your optimal solution. That's the big idea. It's not my idea. I read it in the paper. But once you have this idea, it's solved. Because now you know the matrix apart from a constant factor, but you know that this consists of the known camera matrix and another matrix containing two vectors from the rotation matrix and a translation vector. And the vectors in a rotation matrix are always length 1. And the third vector, which we dropped earlier because the third dimension is always 0 for our points, we know that the third vector must be orthogonal to those two. And we know the object must be in front of us, otherwise we couldn't see it. So T3 is greater 0. And we know that the object is facing us because otherwise we wouldn't see it either. So the scalar product of the third axis and the translation vector must be negative or 0. And if you compare, that's the source code. So after lots of thinking, you end up with very little source code actually. Okay, I haven't included the source code of the singular value decomposition. I just use the singular value decomposition from the Linux Ruby extension. But that's all the code, and at the end you have the extrinsic camera matrix, and then you have enough information to draw a coordinate system like this into your image. And if you want to go over this again, I can recommend Zhengyu Zhang's paper about camera calibration. And I can also recommend a chapter of Ballard and Brown's computer vision book. And the slides are released on the web, by the way, anyway, so you don't need to take notes of the URL and all this. If you can't find them, come back to me later. I put the URL on each slide, but it's not visible. I'm sorry about that. So now I want to give you a small demo with this. So basically, I have a camera here, and it's viewing this marker. I hope it will work. Yes.
For the framework, that means.
So here I'm watching a video, and it always gets properly placed onto the marker. It's a bit dark, but it's still working.
So in this case, what made difference? MySQL, Solaris, and dtrace. They found a lot of trace and picked them one by one.
Oops. I knew you would like it. Except maybe for one person.
Do you agree?
So you can see it really works in 3D. Also, there's a bit of a problem because it's a bit dark in here.
Something that makes difference, but
and I also added some special effects so that it sometimes.
I think it is it.
Does this? Just for fun. All right. Thank you. Yeah, that's it pretty much. So if you have any questions. Yeah. Yes?
There's been a lot of augmented reality stuff coming out with the iPhone, especially with the Compass now. Are you looking into any of that stuff? And it may tie into Ruby with Mac Ruby coming out, allowing Ruby to run on the iPhone, possibly, if you can be compiled ahead of time. So, you could take probably a lot of this library and port it straight to the iPhone and use the camera and the Compass and all the facilities of that to do some interesting applications. Have you thought about that?
I mean, you would just have to call the I/O classes. So you would have, I guess, I don't have a Mac, so I guess the camera input and maybe the display will be different. but it's pretty much pluggable because it only relies on memory objects to exchange data. So you would need to port that part. And as far as I know, ruby-libjit runs on macOS as well. Yeah. Next question.
All of the primitive operations you've created on top of libjit, is that part of that HornetsEye?
Yes. Basically, HornetsEye provides the array classes, and it has some bindings to different I/O libraries. So that's the other problem you need to deal with when doing computer vision. So at the moment it runs under Linux, and most of it runs, or a lot of it runs under Windows as well, on PCs. So I have I/O for loading images, loading video files, also for displaying, even like hardware accelerated video display under Linux at the moment only, and a Qt4 integration to display as part of a GUI. And then there's array classes which are making use of libjit, and then there's also means of conversion to use Ruby OpenCV or NArray, and I also make use of the fastest Fourier transform of the West library for Fourier transforms at the moment. Yeah.
Sorry, what did you say you were using for the Fourier transforms?
FFTW. This is called the fastest Fourier transform of the West. So the Fourier transform I'm not doing with libjit, I'm just using the FFTW library at the moment. Yeah. There's another thing. This is a comparison with Python and OpenCV. So by using closures, by using lambda functions, you can see that you can save a lot of code and provide a much more concise API. And there's another thing I noticed. I think in order to beat OpenCV and other C++ libraries at performance, it will also be necessary to avoid intermediate results. So I was quite interested when Yukihiro earlier on this morning mentioned this problem. Here's an example. I tried something where you have an array, but the constructor, it will behave differently depending on the thread variable. So the purpose of all this is if you have, for example, if you do two array operations, let's say you compute A plus B plus C. At the moment, my library will compute A plus B and write the result to memory, and then it will do this result plus C and write this to memory. So you could avoid the intermediate result to save some time. So I'm thinking about something like this at the moment to implement in the near future, so that in the constructor you behave differently depending on the lazy variable of the current thread. Then you have a method where you can just say lazy do, and then you do some computations, and then you do end, and then it will, after the end, it will mark all objects as now you have to compute them, and once I retrieve the result of one of these objects, it will do the computation only at that point. That's another thing I'm thinking about at the moment. You also need to deal with Colourspace conversions when you do I/O. Many cameras, almost all cameras, they provide the luminance channel with high resolution and the color channels with lower resolution. So it's split up into gray and into chroma red and chroma blue. So you need to upsample and do these linear conversions. That's another thing you need to do when doing computer vision. Oops. So, any more questions? So, otherwise, thank you for listening to my lecture.